The outline of today's lecture is the states of water, energy in water, polarity, mixtures, properties, measuring stuff in water, and the pH of water. So you'll see how awesome water is. On Earth, because Earth is just that exact right distance from the sun, water exists in 3 possible states. And because it doesn't freeze till 0 and it doesn't boil till 100, it's largely liquid. Although it does exist as a gas, so these clouds are gas. It exists as water. Oh, that looks like a great surfing wave. And it exists as a solid or ice. And indeed, in some places, it exists as both water and ice. 3 possible states. So the thing about the states of matter is that as they change from a solid to a liquid to a gas, they increase in energy. And the reason is that at a solid state, those molecules just are not moving around very much. In a liquid state, they're moving around more, and in a gaseous state, they're moving around quite quickly. And this kind of energy of movement is known as kinetic energy. So I would like to talk about that. A little bit, because energy is an important concept. We'll be talking about a little bit later in the next section, but the movement of atoms and molecules is kinetic energy. And that is the energy of motion, because they are always moving. The faster something moves, the more kinetic energy it has. And heat is the product of that kinetic energy. So heat is a product of this kinetic energy. So for example, take your hands, rub them together vigorously. Do your hands heat up? Yes, your hands heat up because the molecules you have just rubbed on the surface of your hands are moving around vigorously. So temperature is a measurement of heat. Temperature measures the intensity of heat. And the heat, in particular, due to the average kinetic energy of the molecules. So water is so fantastic because it has very high specific heat. And that is due to the hydrogen bonds formed because water is polar. So specific heat of a substance is the amount of heat the substance must absorb For 1 gram to increase in temperature 1 degree Celsius.
Miss Morgan,
Yes,
we cannot see your writing.
you can't see the writing.
No,
Oh,
sorry, we cannot keep up.
oh, I see. So you want me to pull it down a bit. Okay,
Please,
yes, we
thank
can
you.
do that for sure. Thank you. I tend to write quite quickly because of years in university. So years in university in a big lecture hall, just writing and writing and writing. And people used to borrow my notes all the time because I took a lot of notes. So yeah, I
I don't
probably
think
have faster writing than most people. What's that?
I don't think that's it. It seems like it just stopped updating to the screen after the sentence heat is a product of kinetic. Like it was showing fine and now it's just the bottom half is
Oh,
blank. It's not like it just didn't
oh,
update
I
it.
see. Well, look at that. Well, that's very odd, isn't it? Let's see. Oh, yeah, it's not moving around. Okay. Huh. Okay. Well, that's a technical glitch, isn't it? Let's see. Okay. Well, I'm going to, nope, it's frozen somehow on your screen.
Can you
Well,
just make a new screen and start again after that spot?
totally. Well, actually, I'm moving my lecture around, but it's not moving on the share screen for some reason. I can't figure out why that is. So I'm going to stop share and then try sharing again, okay? Let's see. Share. I'm going to try sharing it again. See if that works. Okay, there, it's
Yeah,
working now.
it's working now.
Okay. Oh yeah, sorry about that. I have no idea why that happened. I must have pressed something inadvertently somewhere. So go ahead and continue writing. I just, it's funny, I just recorded that whole thing. I wonder if it's still recording. Yes, still recording. So I'll have to do some fancy dancy editing of this video. No worries, I have a lot of experience in that. So one of the reasons we're talking about specific heat is because water has a very high specific heat. Let's see here. Okay, where to go? Come on, man, don't do this to me now. Yep, this is really weird. Usually I just double tap my pen and I can write. I can't write right now. Okay, well, I'll just talk then. Water has a very high specific heat. That means that it takes a lot of energy to evaporate it. And it also means that it can absorb a lot of that energy. So that's why when you live along the coast, where there's a lot of water, the ocean, it moderates the temperature. Now, we don't get these huge fluctuations of temperature. And that's because water is polar. Water is polar, which means that it's slightly a negative on one end where the oxygen is, and it's slightly positive at the other. So oxygen is highly electronegative, so it tends to pull the electrons towards itself, and that's why water is polar. And the polarity of water results in hydrogen bonds. Oh boy. Hang on, hold everything. Uh, uh, we're having some technical difficulties here. Okay, that's enough of that. Water, water. That's all we want. We just want to talk about water. Okay. Yeah. So in a sample of water, some of those water molecules will be dissociated. Not very many. One in like 554 million might be dissociated. In this case, water has swapped hydrogen. We have a hydronium ion and a hydroxide ion. Often what we get is water dissociating into just simply a hydrogen ion and a hydroxide ion. And that occurs on an ongoing basis, but in a given sample, it's quite rare to have a dissociated water molecule. One of the advantages of having water as part of our body, indeed about 70%, is that it's stable. And it leads to what is known as evaporative cooling when you sweat. So remember we said that molecules that move around very quickly tend to be hotter because they have more molecular motion. So when you sweat, the water molecules that evaporate as gas, well, they're very highly active. They're very warm. But the water that's left behind is cooler as a result because it isn't moving around as much. And that's called evaporative cooling. Sorry, I should also add there that we as endotherms have to regulate our temperature internally. And it turns out to be not that hard because of water, because it does take a lot of heat to really warm up water. So for example, if you put like a metal pot on your stove with water in it, you can touch the water for a while and it's okay. But if you touch the metal, you'll burn your hand. And so the specific heat of metal is very low, but the specific heat of water is high. So it's starting to heat up, but the temperature isn't going up because it's not moving around as quickly. And of course, steam is hotter than water. When you boil water, steam is very hot, and that's because it's a gas and it's moving very rapidly. We're also lucky to have water as our substance or liquid of life because it's a really good solvent. You might have heard the term universal solvent. Well, the reason that water is such a good solvent is because, guess what? It's polar. Polarity of water is just remarkable. It's polar so that you can see here we have a sodium ion and a chloride ion. The sodium ion has water all around it. This is called a hydration sphere. And you can see that the oxygen, which is the blue part of the water molecule, is facing the sodium. In other words, it's separating the sodium from the chloride because there's so many water molecules with slightly negative oxygens to them that they surround the sodium, the positive charge, because the negative charges of the water molecules are attracted to the positive charge of the sodium. So anything with a charge is readily dissolved in water. Water has a very interesting shape, and we're going to talk about solutions, colloids, and suspensions, measures of concentration, acids, bases, and pH. So the shape leads to its ability to be a good universal solvent, although it doesn't dissolve everything. But also, we can describe our body fluids, our blood, urine, interstitial fluid by talking about solutions, colloids, and suspensions. So these are all mixtures. Dissolving sugar in water gives you a solution. It gives you a solution because the sugar is dissolved and it remains suspended. It remains suspended. The beach, however, is a suspension because the sand, when it's mixed with water, it settles out because the sand is quite heavy. Milk is a colloid. It has larger particles than a solution, but they don't settle out like proteins. So if you remember the chemistry demonstration that Robin gave, she had the white, supposed to be milk, but it wasn't. But the particles in it were precipitates, but they didn't settle out. So water's property of polarity and its ability to form hydrogen bonds with neighboring water molecules gives it these properties: adhesion and cohesion. Adhesion is when a molecule adheres to a similar or a different molecule than itself. Cohesion is when a molecule adheres to itself. So water has a lot of cohesion. Water loves itself because water is polar, and the oxygen is always attracted to the hydrogen, and they make hydrogen bonds. So what you're seeing here is an example of both cohesion and adhesion. So the water is indeed traveling up the stem into the petals. Indeed, water travels from the roots of extremely large trees to the leaves at the very top. The tree can even be like 350 feet high. And the water comes from the bottom, it comes from the soil. So how is that possible? Well, what happens is that at the top, at the petals, and in trees, at the leaves at the top, water is slightly evaporated. And when it evaporates, it pulls on the water molecules below it. So these upper water molecules are pulling on lower water molecules, and those are pulling on the water molecules underneath, and they're pulling on water molecules below them. And so it's just kind of a tugging thing. So water molecules are pulling each other up to the top of the tree. So why is that important for you and I? Well, we have capillaries. So the thing about plants, which I should tell you before I carry on, is that the water travels up tubes, and the tubes are just cells that are stacked on one another, and they have pores between them. So your capillaries are also very, very narrow. Indeed, a capillary will only let the size of your blood cells through, one at a time, so singly. So capillaries are very small. So, but blood is pushed through your capillaries with blood pressure. So there's some hydrostatic pressure there. But also water adheres to osmosis. And so that's another force that keeps water moving throughout your body. But your blood has to get back to your heart somehow. And so it does that because it has cohesion. It tugs on other water molecules. So even against gravity, with the help of your skeletal muscles, of course, as well, water can go against gravity because it pulls on itself. It tugs on the water molecules below it. And that's called capillary action. Another property arising from the polarity of water and the fact that it loves itself, it makes hydrogen bonds with itself, it's very cohesive, is surface tension. So surface tension is a measure of the force necessary to break the surface of a liquid. And it's related to cohesion in that the surface water where this water strider is standing is a little bit like clingy cover or like a saran wrap or something, because it would like to stay with itself more than it would be evaporated into the air. So that's why the water strider can actually stay on the top of the water. So water's polarity also gets involved in felicitating and participating in chemical reactions. So it ionizes acids, it ionizes salts, it ionizes itself, so it can separate into hydroxide and hydrogen ions. And it's very important for the transport of molecules. So in the blood, your molecules of interest, your electrolytes, your hemoglobin, your proteins, they have to be dissolved in order to be transported into blood. And in order for anything to pass across a cell membrane, it has to be dissolved. So it's very important for that. And it's involved in two processes that we're going to talk about when we get to organic molecules, which is hydrolysis, the breaking down or digestion of molecules, and condensation, also known as dehydration synthesis, the synthesis of molecules in the body. We've looked at weight per volume. The way we can measure concentration or make up concentrations of solutions is by weight per volume percentage or molarity. Molarity is the number of moles of solute in a solution. So to make 1 molar solution of sucrose, we slowly add 1 mole of sucrose, which is 342 grams, in a beaker until the volume is 1 liter and all the sugar is dissolved. I hope this is making sense to everybody. So one day you may have to make concentrations based on moles. You might make IV solutions. If you're doing weight per volume, an IV saline solution would have 8.5 grams per liter of salt, for example. A percentage is used with dextrose solutions. So an IV of D5W is 5% dextrose in distilled water. And molarity is the number of moles. Yeah. So how do you get molarity? Molarity is simply a mole is simply 1 mole of a solution is the number of atomic mass units in grams. So it's quite simple. In this case, with sucrose, it's 342 grams. It is indeed 342 atomic mass units. So all you have to do is calculate the atomic mass units of a molecule, that is the number of protons and neutrons, and then just change that to grams and you have a mole. And what I think is really interesting about moles of any element is that a mole of any element has the same number of atoms, Avogadro's number, which is, oh my gosh, something 3 times 10 to the 23 or something like that. An enormous number of atoms. Indeed, if those atoms were kernels of popcorn, they would cover Canada to a depth of 9 kilometers. It's an enormous number of atoms. There's the same number of atoms in a mole of any given substance. When we have electrolyte concentrations what we're doing is we're adding the charge of the solution. So, and we call that milliequivalents instead of milliliters. So we're just adding a charge. So 1 millimolar concentration of sodium, for example, gives us 1 milliequivalent per liter. And that's because of the charge of 1 positive charge. Acids, bases, and pH, are they important to us? Well, yes. We need to maintain a particular balance in our bodies, our pH balance, which is actually a little bit basic. Yeah. An acid is a proton donor, a base is a proton acceptor, and pH measures the concentration of hydrogen ions in a solution. So it's based on a logarithmic scale. You don't have to remember exactly how pH is measured. What is most interesting is that our body uses buffers to resist changes in pH. We have buffers in our blood. Here's the pH scale. It shows blood as being a little bit more basic, probably 7.2 or 7.3. As we get more basic, our bile is quite basic. Things like bleach, magnesia, those are basic. Acidic things are, well, pure water would be 7. Rainwater, interesting, is about 6. Cow's milk and saliva is more acidic. Urine is more acidic. Coffee, of course, tomatoes, soft drinks, those are all slightly more acidic. And so now I'm going to stop the lecture and we'll carry on.